Now, I want to start off tonight just taking a quick look at MyMathLab. I am hoping you guys have all made it into MyMathLab. You will notice if you go in there, if you've gone in there since 3 o'clock this afternoon, on your little assignment list on your to-do list here, there will be this little yellow or orange square with this quiz 1 on it. If you click in, the homework list should still look the same, but on the quizzes and tests, you'll notice quiz 1 is now at the top of the list. So that those quizzes will appear always at 3 o'clock on the day of class, 3 o'clock on Wednesday. And this one, they'll all be there until the next day at 11:59 p.m. So you have 33 hours to complete the quiz, a window to do the quiz. So for quiz 1 is out there, and you have from now until tomorrow night at 11:59 p.m. to do it. Now, unlike the homework, you don't have all those assists. You don't have the show me a hint and do an example and all that stuff. So make sure you're ready. Go back through the homework. You can always go back through the homework and redo problems and try them without the little assists and see if you can do them to make sure you're ready for the quiz. The quizzes, as you can see over here, you get 2 attempts, and that's not 2 attempts per question, that's 2 attempts at the whole quiz. So unlike the homework where you can check your answer after every problem, on the quiz, you can't submit it until you've put in an answer. Well, I mean, you can submit it, but it'll mark the ones wrong that you didn't answer. So you don't submit it until you've put in an answer for every question on the quiz. Then you can submit it, and then it'll give you a summary of which ones you got wrong and which ones you had right. You get a second attempt as long as you can complete that second attempt before 11:59 p.m. on Thursday night. No use not to unless you get a perfect score the first time, because the system will automatically take your highest score. So I will remind you again at the end of class that there's a new quiz out there today, but just to give you a little forewarning. Does anybody have any questions on MyMathLab and how it works, or having any problems with it? You had some problems? Sometimes it depends on what web browser you're using. I know it tends to have some issues with, for me, it runs faster on Chrome than it does on Firefox. And it depends from computer to computer. Here at school, it loads better on Firefox for me. At home, it doesn't load on Firefox. I have to load it on Chrome. So it's a matter of playing around with which web browser you use. Sometimes you have to go in and clear your web history on the computer and your cookies and stuff like that to make it load. Other times, because it is a self-renewing site, it regenerates every few seconds. If you have a really slow connection, sometimes it won't let you, it doesn't connect. So I know sometimes if the network is busy, I can't connect from home because my connection slows down too much. If you're working on the homework and it did that to you, I know the due date I think is at 6 o'clock tonight. The homework, if you keep working past that due date, it's going to give you a warning saying there's going to be a penalty for if you continue. It'll give you a choice to practice or try to improve your score. And if you click on improve score, it'll give you a warning that it's going to be a point penalty for it. Don't worry about that. Just go ahead and click it and keep working on it. That way I can see that you put in the effort to finish it even after the due date. Any other questions or issues with MyMathLab? Yeah. Yep. Okay. And I could not take an answer, then I'm like, okay, I just took nothing 3 times and got it wrong, and it gave me a new problem. And I thought maybe that one would. Yeah, it still didn't? Still didn't. Did you try to go back a question and come back to it and reload it? Okay. Did you know how to do the question? Okay. That's what matters then. As long as, because on the homework isn't graded for accuracy. When I look through the grade book, when I look at the homework, if you have at least an 80%, you just automatically get full credit for it. If it's below an 80%, I then can go in and I can look and I can see how much time you spent on it. And I can see which questions you attempted, and I can actually see every attempt on each question. So something like that where I can see it just didn't let you access it, that's not going to hurt you. But yeah, the homework to me is a learning tool. I grade it only so that people will do it. But as long as you're putting in the time and effort on it, you're going to get full credit for the homework. Homework is 20% of your grade. Any other questions or issues with MyMathLab? Okay. Okay then, well, it's time to hit our new material. We left off last week, we were talking about numbers, working with real numbers, fractions, decimals, integers. This week, it's time to look at algebra. And we're going to start talking about variables. And a variable, put simply, is nothing more than a letter used to represent some unknown number. Usually we think of the letter X as being a variable, but it can actually be any letter. There are several uses of variables. One use is in formulas. For a formula, we might have something like F equals MA. But whenever we have, first of all, whenever we have two letters written right next to each other like that, that's implied that that's multiplied, M times A. So later we might be told that M equals 12 and A equals 30. So now we can come back and replace those. M is 12, A is 30. 12 times 30 is 360. So F is 360. So that's a formula. In a formula, each of these letters, each of these variables can take on pretty much any value within, reason of whatever that is they're supposed to represent. The next representation of a variable is simply to state rules. And in this case, what it is doing is just representing a generic number. So one of the things, if this were a formal algebra course, we might talk about the commutative property. Commutative property for addition says, if you are adding A plus B, that should give you the same answer as if you add B plus A. So again, it's stating a rule. It's just holding that place, and it could be any number. Either one of those variables could be any number we want it to. A third application is going to be an unknown value in an equation. Now, this is slightly different than the first one up here. I mean, this one up here, yeah, this is an equation, and those are unknown values, but we can put any value in there that those variables happen to take on. Down here, what this is talking about is something like this. 3x plus 7 equals 25. We don't know what value x is, but it does have a value. So it has a set value. We just don't know what it is. So we're going to need to find it. So to start off then, working with these things tonight, I want to take a look at just working with the variables themselves and some operations with the variables. If you recall, we talked about something like 4x in terms of numbers, where the 4 is going to be the count. Just like having 4 inches or 4 cows or 4 sevenths, that tells us how many we have. The x is our name. And to review, for addition and subtraction, we can only combine numbers that have the same name. So for addition and subtraction, we can only combine things that have the same name, 4x and 7x, but not 4x and 3y. We always combine the counts no matter what operation we're doing, but when we add or subtract, we then keep the same name. So what that means for addition and subtraction, if we have 4x plus 7x, those have the same name, so we can combine them. We're going to combine the counts. What's 4 plus 7? 11. And then we're going to keep the same name, so it stays x. On the other side of that, if I had 5x plus 2y, what do I get? Trick question. It's 5x plus 2y. They have different names. They do not have the same name. So I can't combine those with addition or subtraction. So it stays 5x plus 2y. When we do multiplication or division, however, we don't need the same name. We could multiply feet times pounds and get foot pounds. We could multiply 1/7 times 2/3 and get 2/21. So we do not need the same name. And as in any operation, we're going to combine the counts, but in multiplication and division, we also combine the names. So if we had, come on, 4x times 7x, we're going to combine our counts. What's 4 times 7? 28. But we're also going to combine the names. X times x is x squared. So back to that 5x and 2y. If we have 5x times 2y, can we combine them? Sure. When we multiply or divide, we do not need the same name. Oops, where'd my 5 go? So we're going to combine the counts. 5 times 2 is 10. Then we also combine the names. X times y is xy. So again, it's not special rules for our algebraic numbers. It's the same rules that we use for fractions, decimals, whole numbers. It just looks a little different because of the variables. So let's focus in on addition and subtraction here for a little bit. So let's look at something like this. Those all have the same name, so we can combine them. Order of operations does apply to our algebraic numbers, just like our whole numbers. Going left to right, we're going to do 5x plus 7x, which is 12x. Now, we can either think of this as 12x minus 13x or 12x and a negative 13x. Either way, 12 and negative 13 combine to make negative 1. So we can write that as a negative 1x, or we could just put a negative x, means the same thing. If I write x, you can think of that as the same as if I say an inch. We know that it means 1 inch, just like that would mean 1x. So whenever you see an x without that number in front, without a coefficient, they call it, it is implied to be 1x. Now, we said that if we had 9x plus 3y, that we can't combine those with addition or subtraction because we have different names. But that doesn't mean that there's nothing in the problem that can be combined. We might have something like this. So even though there are different names, there's more than just the x here. We can still combine the things that do have the same name. So 9x and 4x make 13x. Good. Now here we have 3y. It's a positive 3y. This over here is a negative 5y. That sign goes with the number that comes after it. So that can be thought of as minus 5y, or it can be thought of as a negative 5y. It's usually easier to think of it as a negative 5y. So 3y and negative 5y make negative 2y. So that turns out to be, combines to make 13x minus 2y. Now, if you were looking at some keywords to tell you what to do here, the word that would often be used, the command that would often be used for this would be simplify. Simplify means to combine what you can. Often, when you simplify, you end up with things like this, where it does not get down to a single term or a single letter. The single biggest mistake I see students make on problems like this is they try to combine things all the way down to one thing, and you can't do that in many cases. This has to stay 13x minus 2y. What if we have 4a minus 5b minus 7a plus 9b? So what can we combine here? 4a and negative 7a give us negative 3a. What else can we combine? Perfect. Negative 5b and 9b make 4b. Now there's something missing there. What do I need? Yeah, I need something to link them together. And since that's a positive 4b, we put a plus in front of it, a plus to link them together. Remember, this symbol or this operation goes with the number that comes after it. So it's a positive 4b, it's a plus that we put in there. That's a very good question. Math grammar says that you should put variables, one of two things. So we just lost, who'd we lose there? We just lost Lady Smith. Okay, if they're not back in a couple minutes, I'm gonna have to go see what's going on there. So anyway, math grammar says one of two things for variables. If it's different variables, they should be alphabetical order. Now, does that mean 4b minus 3a would be wrong? No, it's still the correct answer. It's just more proper to write it as alphabetical order like that. If it's a single variable, we can have one variable with different powers. Math grammar says to put them in descending order. Descending order means highest power down to lowest power. Yeah, exactly. Yeah. There's Lady Smith. Can you see my content now that you're back up? Yeah, okay, good. Okay, so let's take a little bit of a review of the structure of our numbers from last week. And actually, you know what, to lead into that, let's talk about exponents first. We talked about this a little bit last week, I think. Something like 5 to the third power, what does that mean? Not 15. 5 times 5 times 5. There you go. That's actually a very common first answer, though. So that means 5 times 5 times 5. It multiplies up to be 125. On your calculators, many of you have a button that looks like this. It's called the caret key. Others may have a button that looks like this, x to the y, or it might be y to the x. To enter that power on your calculator, you do 5, press whatever key you have, and then enter 3, and hit equals. And it should spit out the 125. If you have your calculator with, I'm going to have you try a couple just to make sure you've got it down so that they work. So let's have you do 2 to the power of 11 and see what you come up with. Everybody get 2048? Okay, perfect. If you don't have a calculator yet, you'll be fine through the first 3 or 4 weeks. Somewhere around week 5 or 6, or for the next 3 or 4 weeks, I should say, somewhere around week 5 or 6, having a scientific calculator will be essential. Your cell phone calculators will not do some of the long formulas in the last 6 or 7 weeks of the course, just so you're aware. And powers is a very important calculation in those formulas. Okay, so let's look at something like this. X to the third power, of course, means x times x times x, or 3 x's multiplied together. So what if I have x to the third times x to the fifth? Well, x to the third is 3 x's multiplied together. X to the fifth is 5 x's multiplied together. If I multiply them all together, how many x's do I have? 8 of them, and they're all multiplied together, so that's x to the 8th power. Now, I heard somebody over here say the answer right away. They know that the rule is what? When you're multiplying exponents with the same base, they're both x in the base here, you're going to add the powers. 3 plus 5 is 8. So if I have y to the 7th times y to the 14th, I'm going to get y to the 21st. Perfect. I do have to be a little bit careful because I'll catch people with this one. Z to the 5th times x to the 12th. Does that come to the 17th? No. I can multiply those, but the powers aren't going to combine because they have different bases. The only thing I would change there is our math grammar says alphabetical order. So the x to the 12th will go first, z to the 5th will go last, and there's no need to put multiplication between them. It's just x to the 12th, z to the 5th. I can divide x to the 5th divided by x to the 3rd. Perfect. There's going to be 5 x's multiplied together on top, 3 on bottom, and with a fraction we can cancel out or divide out common factors. We can divide out 3 x's and we'll be left with x squared on top. The shortcut, as you can see, is to do what when we divide exponents? Subtract the powers. 5 minus 3 is 2. So if I had y to the 28th divided by y to the 17th, I'm going to get y to the 11th. Perfect. 28 minus 17. These rules apply even if we have more than one variable. We might have x to the 5th, y to the 3rd, times x squared, y squared. And to work with that, we go each variable on its own. X to the 5th times x squared. What are we going to get? Perfect. X to the 7th. 5 plus 2 is 7. Y to the 3rd times y squared. Y to the 5th. Perfect. 3 plus 2 is 5. I could throw numbers in there even. 3x to the 7th. Y squared z to the 4th times 8 x to the 4th y z squared. So perfect. Yeah, just like any other number, we're going to combine the counts. 3 and 8. Now we are multiplying, so we still have to multiply those. 3 times 8 is 24. Then we'll look at the x's. X to the 7th times x to the 4th. X to the 11th. Now y squared times y, we think of it as y to the 1. Y to the 3rd. 2 plus 1 is 3. And z to the 4th times z squared. Z6. Perfect. Same goes for division. We can have multiple variables. X to the 9th, y to the 5th, divided by x to the 4th y. Well, we're going to get x to the 5th. Very good. 9 minus 4 is 5. And y to the 4. Yes. You think of this as 1. 5 minus 1 is 4. So x squared, y to the 4th. We can even throw numbers in there. We'd have 36, x to the 8th, y squared, z to the 5th, over 9, x to the 5th, y squared, z to the 4th. So again, just like any number, we're going to divide the numbers. So my 3 disappeared. What is 36 divided by 9? 4. Then we're going to divide the variables one at a time. X to the 8th divided by x to the 5th. X to the 3rd. 8 minus 5 is 3. Y squared divided by y squared. It cancels out. The y's disappear. They divide out. Z to the 5th divided by z to the 4th. Yeah, we do 5 minus 4 is 1, so we could do z to the 1, but that's just a z. So either way, if you left it as z to the 1, it would not be wrong. It's just more proper to list it as just z. We could have something like this, x to the 3rd to the power of 5. That's saying we have 5 of these x to the 3rds multiplied together. Well, each of those is 3 x's multiplied together. How many x's do I have multiplied together there? 15. Good. When we have a power of an exponent, a power of a power, what we do to combine the powers is multiply them. So if I have y to the 7th, the power of 11, I get y to the 77th. Perfect. If I have 3 x to the 5th, y to the 9th, to the 4th power, I still have to do 3 to the 4th power. What is 3 to the 4th power? 3 times 3 times 3 times 3 is 81. So 81. And then I do have to do the variables. X to the 5th to the power of 4 is x to the, 5 times 4 is 20. And y to the 9th to the power of 4 is y to the 36. 9 times 4 is 36. Good. Now that we have that knowledge of powers behind us, we're going to step back and we're going to take a look at place values with our whole numbers again, only a slightly different angle to it. This is the ones, tens, hundreds, thousands, 10,000s, and so on. Well, our place value system, our number system, is referred to as a decimal number system, which stands for a base 10 number system. What that means, you've heard me use that word base before tonight. What that means is each of the place values is an exponent. In an exponent, there are two parts. There's the base and the power. So x to the 5th, the base is x, the power is the 5. Well, our place values are base 10. They are exponents with a base of 10. The ones place is 10 to the power of 0. Anything to the power of 0 is 1. 10 to the power of 1 is 10. 10 to the power of 2 is 100. 10 to the power of 3 is 1,000. 10 to the 4th is 10,000. 10 to the 5th would be 100,000, and so on. Each of those place values is a power of 10. Now, we talked about the full form of a number, taking something like 237 and writing it as 2 hundreds and 3 tens and 7 ones. That's writing it out with words for the place values. But we could also write it out with exponential place values. So instead of 2 hundreds, this would be 2 times 10 squared. Instead of 3 tens, it would be 3 times, well, 10 to the 1, we don't need the power of 1 there, do we? Plus 7 times 10 to the 0 is just 1, so we'll just put 7. 7 times 1 is just 7. So that is one way of writing that number out in expanded form. With that number written out that way, it now becomes a little more obvious how our algebraic numbers work. Because I can have an algebraic number that is 2x squared plus 3x plus 7. What you see has happened here in an algebraic number, instead of the place values being powers of 10, they're now powers of x. A lot of people, when they see this, they think it is 3 separate numbers, but it really isn't. It is one number with 3 digits. Now, the official name, the formal name for it is a polynomial. The generic term is expression. So it's a polynomial expression would be its full name. But it really is nothing more than just an algebraic number. The place values are powers of x instead of powers of 10. Because of that, it behaves exactly like, in many ways, exactly like any other number. There are 2 big exceptions. First of all, it is always written out in long form. There is no abbreviation like 237 that we can write it in. Second, in a whole number or an integer, either every digit is positive or every digit is negative. Up here, 237, that's a positive 200s, a positive 3 tens, and a positive 7 ones. So every digit is positive. If we had negative 438, well, that would be a negative 400s and a negative 3 tens and a negative 8 ones. Every digit is negative. In an algebraic number, each digit is free to be positive or negative. I can have 7x squared minus 4x plus 9. And our third difference is that in a whole number or an integer, each digit can only have, or each place value can only have one digit in it. In an algebraic number, we can have more than one digit in a place value. We could have 5x squared plus 13x plus 27. There's two digits in each of those place values. It doesn't matter in our algebraic numbers. So let's look at some operations. If I have 4x squared plus 7x plus 3. Now I'm putting that in parentheses. We're used to seeing parentheses telling us that we have to do something there first. We saw with our negatives that it also can be just separating a number to specify that that's a number and not an operation along with it. So those parentheses there, that's just saying that that is one number by itself. And we're going to add that to 3x squared plus 4x plus 2. Now, many of you, if you had a formal algebra course, were taught just drop the parentheses and combine what they call like terms. Well, all that is just our long addition, just like any other number. I can write out the first number, 4x squared plus 7x plus 3. And then the second number I'm going to put underneath it, making sure I line up the digits. So the 3x squared goes under the 4x squared. The 4x goes under the 7x. The 2 ones goes under the 3 ones. And we are adding here, so we're going to be adding down each column. And now we can combine each column, each like place value. 3 and 2 make 5. It's positive, so I'm going to put plus there. 7x and 4x make 11x. Again, it's positive, so I'm going to put a plus in front of it. 4x squared and 3x squared, 7x squared, and that's it. It's the exact same addition process that we use for whole numbers. Now, it can be confused a little bit when we throw in negatives. So we might have 5x squared minus 13x plus 7 plus 3x squared plus 9x minus 11. Again, we're still just going to write this out one above the other like we would with whole numbers. Lining up the x squareds and the x's and the 1s. And we are still adding down each column here. We just have to deal with the negatives. What is 7 plus a negative 11? Perfect. That's a negative 4. What is negative 13x plus 9x? That is negative 4x. 5x squared plus 3x squared. 8x squared. Now, I cannot say this enough. You're done there. Stop. Every semester I'll have students that look at that, oh, 8 minus 4 is 0, so just 0. You cannot combine these anymore because what's left here is addition and subtraction. These are different place values. Trying to combine those would be just like taking something like 365 and saying, oh, I'm going to combine the 3 and 6 to make a 9. You can't do that. They're different place values. Same thing here. Subtraction works the same way then. I might have 8x squared plus 5x plus 13 minus 3x squared plus 9x plus 7. Again, just like whole numbers, we're going to line them up, one above the other. So I'm going to write the 8x squared plus 5x plus 13 first. I'll put the second one down below. 3x squared plus 9x plus 7, and now we are subtracting. What is 13 minus 7? 6. It's positive, so I'm going to put a plus in front of it. 9x minus, or 5x minus 9x? Negative 4x. Good. And 8x squared minus 3x squared? 5x squared. Good. Well, in front you wouldn't have to, but here you do. Otherwise, there's nothing connecting them together. So that plus has to be there. I mean, up front you could put a plus 5x there too, but that's not, you don't have to have it there because there's nothing in front of it to link it to. Where subtraction gets messy is when we bring the negatives into the subtraction. We might have, now there was a negative here as a result, but all of the digits we started with were positive here. It's when one of the digits are negative to begin with or more. We might have 3x squared minus 9x plus 5 minus 7x squared plus 8x minus 11. So we're going to go ahead and write these out one above the other. 3x squared minus 9x plus 5. 7x squared goes under the 3x squared. Positive 8x goes under the negative 9x. The negative 11 under the 5. And we are subtracting. 5 minus a negative 11. Now what helps me is I always write these off to the side. 5 minus a negative 11. That becomes 5 plus 11. So 5 minus a negative 11 is a positive 16. Remember last week we talked about the negatives? Remember last week we talked about the negatives. 7 minus 3 means 7 plus the opposite of 3, so plus a negative 3. So we have 5 minus a negative 11. It becomes 5 plus the opposite of negative 11 is positive 11. Yes? Okay. Now, I'm going to mention that in just a second. Yep. So now here we've got the next one, we've got negative 9 minus 8. So negative 9 minus 8 becomes negative 9 plus a negative 8, which is negative 9 and negative 8 is negative 17. They both go the same direction. And 3 minus 7, positive 3, negative 7 is negative 4x squared. Now with addition, we had said you could just drop the parentheses and combine the terms that have the same power, or what they call like terms. One of the tricks that is taught with subtraction is, they call it distributing the negative. You'll understand the word distribute here in a little bit. As you change the sign of every number in this second one. So this is going to become negative 7x squared. This is going to become a negative 8x squared. This is going to become a positive 11. And then we can add. So then it would be 5 plus 11. That gives us the 16. Negative 9 and a negative plus a negative 8 is a negative 17. 3 plus a negative 7 is a negative 4. You don't like that way? You like that way better? It is a shortcut. What it is rather than changing each one separately like I did here, it's changing them all at once right there. to plus the opposite. Again, as I warned you before, the hard part is the negatives. Multiply. The second one? Okay. And whatever way works for you, feel free to use. That's why I try to show stuff in a couple of different ways. On to multiplication next. We've already looked at things like 4x to the fifth times 7x to the third. What are we going to get there? Yeah, 4 times 7 is 28. X to the, good. X to the fifth times x to the third. When we're multiplying exponents, we add the powers. 5 and 3 add to 8. So 28x to the eighth. But what if we want to do something more than multiplying single-digit numbers? Like if we have 7x times 3x plus 5. Well, again, this is similar to what we do with whole numbers. If we had 3 times 42, what we were taught to do there, if we were doing this out the long way by hand, is 42 on top, 3 on bottom. I always put the number with the most digits on top and the fewest digits on bottom. Well, then it's 3 times 2 is 6. 3 times 4, 12. So 2 carry the 1. The same thing can happen here. 3x plus 5 times 7x. What is 7x times 5? 35x, and that's a positive, so I put a plus there. 7x times 3x? 21x squared. It's the exact same multiplication as we had with our whole numbers. Now, most of us have probably never seen it done out this way. You've probably always seen it with something, a word I used a little bit ago, distributing, which is just a shortcut for what we did here. What they did, instead of writing it vertically like you would to multiply, they're just going to take the 7x through the parentheses. What is 7x times 3x? 21x squared. And then the 7x times the 5, positive 35x. We get the same answer. The distributing takes a little less room. It might be a little quicker and easier. Okay, that's a great spot to take our break. It is 6:19 on the computer's clock here. We will come back in 10 minutes at 6:29. So we can distribute like that, or we can do the long multiplication. Let's do a couple more examples of that. I'm going to have you try one in your notes, actually. So let's do 5x times 4x minus 7. I'm going to have you try that one and see what you come up with. We'll talk about it in a few. Okay, so I'm just going to do it with distributing. 5x times 4x is 20x squared. Then 5x times negative 7, negative 35x. Good. Now we can get a little worse than that. It might look like this. Tell me what to do. Perfect. 8x to the third times 7x squared is 56x to the fifth. And then, okay, 8x to the third times 5x is a positive 40x to the fourth. It can get a little worse still. Like something like this. This is just an order of operations problem. This is exactly the same as having something like 19 minus 3 times 12 minus 10 plus 7. We have to do what's in the parentheses first. Now, if we look at this set of parentheses here, is there anything we can do inside that set of parentheses? The answer is no. So when we see a parentheses, it usually means do something here first. And when we see them, there's two questions we have to ask. The first one is just what we asked. Is there anything we can do inside the parentheses? And in this case, that was no. The second question is there anything that needs to be done to the parentheses? And in this case, it's being multiplied. Now I'm going to give you a warning. What is it being multiplied by? Okay, you guys caught it. It's a negative 3x squared. So let's go ahead and multiply that. Negative 3x squared times 4x to the third is negative 12x to the fifth. Good. Negative 3x squared times negative 7x. Positive 21x to the third. Now the rest of the problem stays the same. The 9x to the fifth hasn't changed, and the plus 8x to the third has not changed yet. What can we still do now? Perfect. We can combine 9x to the fifth and negative 12x to the fifth make negative 3x to the fifth. We keep the same name when we add or subtract. 21x to the third and 8x to the third? Positive 29x to the third. Good, x cubed. And that's it. That is as far as we can go. I'm going to have you guys try another one in your notes. You make it sound horrible. It only hurts for a little while. I'll have you try that one. See how it works out for you. Let's see how you did so far. So again, order of operations. We have two sets of parentheses. We're going to work left to right. So the first one here on the left. Anything we need to do inside there? No, nothing we can do inside. So is there anything? Because this is x squared and then this is no x. They have different names, different labels. So we cannot combine those. Good question. Is there anything that needs to be done to the parentheses? Well, we have a number in front of the parentheses with no symbol there, so that implies multiplication. When we're multiplying, remember, we don't have to have the same name, so we can multiply anything. So 4x to the third times 2x squared is 8x to the fifth. Very good. Now 4x to the third times negative 5. Negative 20x to the third. See, you can do this. The next set of parentheses there, is there anything that we can do inside that set of parentheses? No, they have different names. We have x and we have 1s. So now that is multiplied by not 3x squared, but negative 3x squared. Negative 3x squared times 5x. Negative 15x to the third, or 15x cubed. Negative 3x squared times 3. Negative 9x squared. Are we done? No, we have x to the third and x to the third there that can be combined. So 8x to the fifth won't change. Negative 20 and negative 15 make negative 35. We keep the same name, x to the third. Then the negative 9x squared does not change. Yeah, whatever has the same name, we can combine the coefficients, they call it. So the negative 20 and the negative 15 make the negative 35, and we keep the x to the third. Dividing. We've already done the one-digit division. If we had a division like this, 486 divided by 2, the short way to do it would be to just divide each digit. What's 4 divided by 2? 2. 8 divided by 2? 4. And 6 divided by 2? 3. So that's it, 243. Now that seems like a very specific case, and it is, but when we look at algebraic numbers, that's the type of case we look at. We might have 24x to the fifth minus 32x to the third plus 16x divided by 8x. And just like we did over here where we divided each digit separately, because there was no remainders from each digit, we're going to do the same thing here. We'll divide each digit separately. What is 24x to the fifth divided by 8x? 3x to the fourth. Good. 24 divided by 8 is 3. X to the fifth divided by x. We think of that as x to the 1. 5 minus 1 is 4. The next digit then is a negative 32x to the third divided by 8x is negative 4x squared. Good. Negative 32 divided by 4 is negative 32 divided by 8 is negative 4. X to the third divided by x to the x is 3 minus 1 is 2, x squared. And finally, 16x divided by 8x is 2. 16 divided by 8 is 2, and then the x's cancel out. So that's it. So that's it for combining algebraic numbers and operations with algebraic numbers. Our next step is to look at that third type of equation we looked at, or type of use of variable that we looked at. Notice things like this. X equals 7, an equation. So in an equation like that, the key to understanding this thing is this symbol right here. What is that symbol? It's the equal sign. Now here's the tricky part to define. What does it mean? Okay, it's hard to define it without using the word equals, isn't it? Go ahead. Same as is 1, yep. The right is same on right and left. Yeah, it means the same as, or has the exact same value as. What's on one side has exactly the same value as what's on the other side. In fact, you can think of it like a balanced scale. What's on one side of the equal sign exactly balances what's on the other side of the equal sign. Now, all equations start in this form that we have here, as x equals a number. And they're built up from there. One of the things we could do to build onto it, well, we could use any of our operations that we use. So far we have addition, subtraction, multiplication, division, even powers and roots. Let's do addition. Let's add 4 to it. So x plus 4 is just x plus 4. But now this scale is going to tip unless I do what? Add 4 to the other side. I have to do the exact same thing to both sides of the scale. So 7 plus 4 is 11. So what I have done here is built a more complicated equation. Now, normally we're not going to be asked to build equations. We're going to be asked to solve equations. Solving equations means we're going to take that equation and we're going to take it back apart. Get it back to this form here as a variable equals a number. So this equation was built by adding 4. How are we going to take it apart? We subtract 4. Subtract 4 takes that off, leaving us with x. Now, because of this balanced scale again, whatever we do to one side, we have to do exactly the same thing to the other side. So we have to subtract 4 over here as well. 11 minus 4 is 7. So x equals 7. We've solved the equation. We put it back in that original form. Now, we built this equation. So we knew how it was built. so we knew how to take it apart. The tricky part is being able to look at an equation and figure out how it was built. So let's go through a process for doing that. To do that, we're going to look at the equation and we're going to find the equal sign. Right there's the equal sign. From there, we're going to identify which side has the variable on it. Well, that's the right side on this equation. Now we're going to ask ourselves, what is keeping the variable from being by itself on that side of the equation? That's the 7. What operation is attaching the 7 to our variable? Subtraction. So when this equation was built, what was done to our variable, or what was done to x, was 7 was subtracted from it. Well, how do we take that apart? What's the opposite of subtracting 7? Adding 7. We add 7, that piece is gone. We're left with y over there. But to keep that equation balanced, that scale balanced, we must also add 7 to the other side. 8 plus 7 is 15. So 15 equals y, or y equals 15. If we're not sure of ourselves and we want to double check, well, if 15 really does equal y, we can come up here and replace y with 15. So does 8 equal, instead of 15, or instead of y, we're going to put in 15 minus 7. Yeah, 15 minus 7 is 8, so 8 equals 8. Let's look at another example. 5z equals 45. So now again, I realize a lot of you can look at this and know the answer. Well, let's go through the process. Here's our equal sign. Which side has the variable on it? The left, 5z. What's keeping that variable from being alone? The 5. What in the operation is multiplication. Good. The 5 is multiplying it. So to take it apart, we're going to divide it. Dividing by 5 cancels that out. Leaving us with z. What do we have to do to the other side? Divide by 5. The exact same thing. We divide by 5. 45 divided by 5 is 9. Again, if we want to double check, we're going to come up here and we're going to replace z with 9. Instead of 5 times z, it's 5 times 9. Does that equal 45? Yes, it does. So we get the same thing on both sides of the equation. So that is the correct answer. If you haven't learned by now, I never let it stay that simple. It always gets worse. We run into equations like this. 3x plus 5 equals 23. So we find our variable, or we find our equal sign right there. We find what side the variable's on. It's on the left there. When we ask what's keeping x from being alone here, well, there's two things, the 3 and the 5. The 3 has been multiplied, right? And the 5 has been added. So if we ask ourselves what was done to the variable, what was done to x to build this equation, if that x were a number, what would I have to do first? Would I have to multiply it or would I add to it? Order of operations says we first would multiply, right? So when this equation was built, x was multiplied by 3. And then the 5 was added to it. Well, if you think about building something, putting together a piece of furniture you buy or putting together a toy, if you've just finished putting it together, you've just put on that last piece. If you have to take it apart again, what's going to be the first piece you take off? The last piece you put on. Perfect. And the equation works the same way. The last piece that was put on was adding 5. That's going to be the first piece we take off. How do we take it off? Subtract 5. Perfect. That takes that piece off. We're left with the 3x. We have to do the exact same thing to the other side. We subtract 5. What's 23 minus 5? 18. Now we have to take off the multiplying by 3, and we're going to do that by dividing by 3. That takes off the 3, leaving us with x. We do the exact same thing to the other side. 18 divided by 3 is 6. Now we can double check our equation by replacing x with 6. So instead of 3x, it's 3 times 6 plus 5, and we're going to see if that is 23. Well, 3 times 6 is 18, plus 5 is 23. Any questions so far? We'll get there. Don't worry. If it's worse, I'll get to it. That sounded really cynical. I'm sorry. True, but cynical. So something like this. Something didn't work there. Come back here. When we look at something like this, we find our equal sign right here. We go to identify which side the variable's on, and we find the variable, it's the same variable, but it appears twice. So if we're thinking of this as that balanced scale still, I have the 3x and the 2x both on the same side of the scale. If I just push them together and make one big pile, does that change the way the scale balances? No, it shouldn't. They're still on the same side. So what is 3x and 2x? 5x. We still have the positive 6 there, and it equals 31. Now this looks just like what we've been doing. How would we solve that? We subtract the 6 from both sides. 5x equals 25. And then divide by 5. So x equals 5. Now we can go back and put 5 back in if we want to. 3x becomes 3 times 5 plus 6 plus 2x becomes 2 times 5. Does that equal 31? Well, this is 15. This is 10. 15 plus 6 is 21. Plus 10 is 31. So yeah, it does get us there. This one looks similar. The variable appears twice, but there's a subtle difference. What is it? On opposite sides, yeah, we find our equal sign. We go to find where those variables are, and there's one on each side. Can I push them together into one big pile? Not this time. Because they're on opposite sides, we can't put them together because they're not next to each other, not with each other. So what we have to do is literally take one off and get rid of it. Mathematically, the way we do that is we subtract it. Or if it's negative, we add it to get to 0. We do its inverse. Now we can get rid of either one of them if we want to, but it's usually simpler if we get rid of the smaller one. Which one's smaller? 2x. So I'm going to take that off by subtracting 2x. It is now gone. There we go. To balance the scale, we got to make sure we take 2x off the other side as well. Where can we take it from? The 4x. So here we've got 18 equals, what is 4x minus 2x? 2x, and we still have the negative 6, or minus 6. Then what? Add 6, good. So we've got 24 here. The minus 6 is gone, so we just have 2x over here. And divide by 2, perfect. So 12 equals x. We took the equation apart. Now again, let's double check. We'll put that 12 up here. 2 times x will become 2 times 12 plus 18 equals 4 times x will be 4 times 12 minus 6. So we have some work to do on both sides. 2 times 12 is 24. 24 plus 18, I can work on each side separately. So 24 plus 18 is 42. On the right side, 4 times 12 is 48. 48 minus 6 is 42. So we get the same value on each side. How are we doing so far? Drained? On track? Okay. And drained? Yeah. This is the time of night where I start to slow down too. So you might hear me drawling a little bit more. I'll try to speed up, I swear. That's what you want to hear. We'll get you through it. So on this one, what's different? The parentheses. And anytime we see parentheses, it should scream at you, do something here first. Same questions as we said before. Is there anything we can do inside that set of parentheses? No. 5x and negative 2, they have different names. One's an x and one's ones. Next, is there anything that needs to be done to that set of parentheses? It is multiplied by 3. So 3 times 5x is 15x. 3 times a negative 2. Negative 6. Good. Still equals 24. What's next? Add the 6. The negative 6 is gone, so it's just 15x equals 30. And then we divide by 15. So the x is gone, or the 15 is gone. X equals 30 divided by 15 is 2. We can double check. So 3 times in parentheses instead of 5x would be 5 times 2 minus 2 equals 24. Now here we have parentheses. Can we do anything inside the parentheses? We can. So let's do it. 5 times 2 is 10. Well, and 10 minus 2 is 8. Now we can get rid of the parentheses. 3 times 8 is 24. So we have the same value on each side. It can get a little more complicated than that. Oh, let's see. What am I going to put in here? Okay, let's see. 8, 11, 55. There we go. So that one. Do I want to let you try that one in your notes first? I'll take that as a no. If I want to walk out in the parking lot without having to look for revving engines tonight, I should do this one for you. First of all, we combine what we can combine on each side of the equation before we start to do any solving. So we're going to simplify on each side first. So here's our equal sign. We're going to start on the left side here. Well, we've seen problems just like that before with our distributing that we did up above. We have 2 sets of parentheses. We're going to go left to right. This first set here, is there anything to do in there? No. Anything to do to it? Yeah, times the 5. So what do we get when we multiply that by 5? 15x minus 35, or 15x and negative 35. Perfect. 5 times 3x is 15x. 5 times negative 7 is negative 35. The second parentheses, anything to do in there? No. To that. Yes, times negative 2. When we multiply that by negative 2, what do we get? Negative 4x and negative 2. Negative 2 times 2x is negative 4x. Negative 2 times 1 is negative 2. What can we combine over here? Okay, so we've got 15x and a negative 4x make 11x. Negative 32 or negative 35 and a negative 2 make a negative 37. Perfect. Now we have combined everything we can combine on the left side. So now we're going to the right side. So on the right side here, we see parentheses. The first one, we're going right to left. Anything we can do inside that set of parentheses? No. To it? Yes. We're going to multiply by the 3. Perfect. 3 times 5x is 15x. 3 times 1 is a positive 3. So on the other set of parentheses, is there anything to do inside there? No. To it? Yeah, times the negative 5. Negative 5 times 2x plus 3? Negative 10x minus 15. Good. Negative 5 times 2x is negative 10x. Negative 5 times 3 is negative 15. Then we still have that minus 1 on the end. What can we combine? 15x and negative 10x make 5x. Positive 3 and negative 15 make negative 12, and negative 1 is a negative 13. Now, right here, we have reduced everything we can on each side of that equation. Now we can start to solve. However, before we can start taking it apart, we see that the variable still appears on both sides, which means we need to get rid of one of them, right? Which one are we going to get rid of? The 5x. It's positive, so we are going to subtract 5x. Make it go away, leaving us with only negative 13 over here. On the left side, what are we going to do? We got to subtract 5x. 11x minus 5x is 6x. What else? We still have the negative 37 there. Now we can start to solve it, and the first step to solve it is what you said there, which is adding 37. So that's gone. We've got 6x here. Negative 13 plus 37 is 24, positive 24. And then divide by 6. X equals 4. Not so bad? There might be. That one's not too uncommon, though. You like that one? Cool. I mean, it's really just combining all the pieces. It's not anything harder than the other stuff. It's just all of it put together. Still better than a sharp stick in the eye, right? Okay. Debatable? Oh, it's not that bad. Yeah, what's your question? Doing shortcuts, yeah, if there's shortcuts you can do, that is fine. When we do math, there's a lot of different ways to do things That's one of the myths in math is we're always told there's exactly one way to do stuff. And that's not true. There are several ways to do things. For example, I don't think I showed you guys this last week. We have like 457 plus 279. How are we taught to add that? Right to left. 7 plus 9 is 16, so we keep the 6 and carry the 1. 1 and 5 is 6 plus 7 is 13, so we keep the 3 and carry the 1. 1 and 5 is 5, or 1 and 4 is 5 plus 2 is 7. So 736 we get. And that's how we're used to seeing numbers added. That's not the only way to add numbers. Did I show you guys this at all last week? I don't think we had time. Another way that numbers could be added is like this. 4 plus 2 is 6. 5 plus 7 is 12, so 2 drop the 1. 7 plus 9 is 16, so 6 drop the 1. 6 and 1 is 7, 2 and 1 is 3, and 6. I've seen that done. That's one of the ways to do it. I can show you 3 or 4 other ways of adding numbers that'll work every time. Is one of them better than the others? Yeah. Yeah. Well, math is all about patterns. The problem is everybody's mind sees different patterns. To many of us, we look at this and this makes sense to us because that's the way we were taught. But there are some people out there, even if they were taught this way, this makes more sense because that's the way their mind sees things. And when it comes to math, there's several different ways of seeing a problem. Everybody's mind picks a different way of seeing that problem. So whatever way your mind sees and whatever works best for the way you think, that's the way you solve the problem. You do not have to do it my way. I try to do things intentionally a little different than the textbook so that you have kind of the 2 different points of view to look at. I'm not saying my way is better or worse or anything like that. It's just different. So that it gives your mind different ways of seeing it. I've said it before, I say it all the time. The only difference between somebody who's good at math and somebody who's not good at math, 2 big things is the time and effort. It's going to take time and effort to get from struggling to being good. And the second is finding the way your mind sees things. Once you figure out the way your mind sees things and how your mind puts things together, then the way it does math is a little bit easier to learn. If you're seeing stuff in a way that your mind doesn't think, it's never going to make sense. Everybody's mind is hardwired to do math, but not necessarily in the same way. Okay, I'm off my soapbox again. Hopefully that answered your question. Okay. That's one of the things I get really preachy about is we tend to do that, especially in the lowest grades where it's the most important. Nope, this is how you do it. No, you got the right answer, but you didn't do it right. Mm-hmm.
Do it. I'll tell you if it's right or not. You do it your way, and I'll do it my way. I'll tell you if you got the right answer.
Well, you think about it, I would not be comfortable teaching English to somebody because I'm not an expert in English. I know how to write, I know how to make a sentence, I know my parts of speech, but I would not know it well enough to explain it to someone else and make them understand it. The same with math. So why would you expect one teacher throughout all of elementary school to be able to teach everybody every topic and do a good job of all of them? They all have a specialty. And unfortunately, many of them, it's not math. So, okay, again, I slipped back on my soapbox. Other types of equations we run into. Because of this, what we just saw here was solving equations. We run into things that look like this. X over 9 equals, let's see here. Like 36 over 12. Now, a lot of us have been taught shortcuts for solving this. We've even been taught a special name for it, called a proportion. This is just an equation. We have a variable on one side and we have numbers on the other. What been done to our variable over here? It's been divided by 9. So to solve it, what's the opposite of dividing by 9? Multiplying by 9. So multiplying by 9 is going to make that go away. We have to multiply the other side over here by 9. So x equals, well, we would have 36 over 12 times 9 over 1. The 12 and 9 can both be divided by 3 to give us 3 and 4, right? 36 times 3 is 108. 4 times 1 is 4. That actually divides out to be 27. Well, that's a little bit more work than what most of us were taught, isn't it? Most of us were taught to take that x over 9 equals 36 over 12 and do what with it? You were probably taught cross multiply, right? Some of you might have been taught cross multiply and divide. You take the two numbers that are on the diagonal, the 9 and the 36, and you multiply them. Then you divide by the number that's by itself on the other diagonal. Cross multiply and divide. Well, that comes from exactly what we did here. We multiplied by the 9. Now I cross canceled. I didn't have to. It would have been 36 times 9 equals 324 divided by the 12, which still gives us 27. So what we did here, solving an equation, is exactly what we would do to solve it. Just cross multiply and divide is, again, a shortcut. So if I have 21 over x equals 56 over 8, the first thing I have to do is figure out what two numbers to multiply. The two numbers I multiply are the two numbers that are on the diagonal, which are 21 and 8. If I multiply those, I get 168. 21 times 8 is 168. Then what do? Divide by the number that's on the other diagonal by itself. Dividing by 56 gives us 3. X equals 3. You're going to hate this phrase. It doesn't stay that simple. Something like this. 9 over 15 equals x plus 5 over 25. We can't cross multiply and divide here because it's not a variable by itself. There's something extra there. There's two ways we can approach this. Well, there's two easy ways. There's a few different ways, but I'm going to show you two. The first one, we are solving for x plus 5. So x plus 5 equals, and now we can take the other numbers and cross multiply and divide. What is 9 times 25? 225. Divided by 15 is 15. So that's saying that x plus 5 equals 15. Now I have to solve that equation. What do? Subtract 5, so x equals 10. Very good. That's one way I can approach it. No. You couldn't subtract 5 and get 4 over 15? That won't work. No, that doesn't quite work out. You'd end up with 5 over 11, which won't be quite the same as 9 over 15. Or 4 over 11, I should say. It's a good idea, but it doesn't quite work. Because what you're subtracting here isn't really 5, it's 5 over 25. Now, another way we could approach this, rather than cross multiply and divide, is strictly cross multiply. If I go back up to this, any one of these here, I'm going to go back up to this first one. The x over 9 equals 36 over 12. I can do 9 times x, because I'm dividing by 9 here, I'm going to multiply, or 9 times 36. Because I'm dividing by 9 here, I can multiply both sides by 9. 9 times 36 is 324, correct? Well, that's over 12. I can multiply both sides by 12 to get that 12 off the bottom. That would cancel that out and give me 12x over here. That'd be 12x equals 324. Well, what I just did there has a shortcut as well. It's not cross multiply and divide, it is just cross multiply. We multiplied on that diagonal. The 9 plus 36 is 320, or 9 times 36 is 324. Then we multiply the other diagonal. X times 12 is 12x. Because of our rules of equations, those two numbers have to be equal. So 12x has to equal 324. We just have to solve the equation, which would be, dividing by 12 here, which would give us that x equals 27. So for this one here, we can do the same thing. We can cross multiply. I'm going to rewrite that. So 9 over 15 equals x plus 5 over 25. So I'm going to multiply on each diagonal. Here we have 9 times 25 is still 225. Here we have 15 times x plus 5. Those two have to be equal. So 15 times x plus 5 has to equal 225. What are we going to do from here? We only have the parentheses. Anything to do inside there? Nope. Anything to do to it? Times 15. 15 times x. 15x. 15 times 5. 75. I'll give you a freebie on that. Now, how do we solve this? Perfect. Subtract 75. So 15x equals 150. And then we divide by the 15. X equals 10, which is exactly what we had up here. To me, this second way is easier because I'm good at solving equations, but to a lot of people, those equations with parentheses can be tough. So a lot of people like to do this, what we did, where'd it go? There we go. Where you just take this and set it equal to whatever you get when you cross multiply and divide the other pieces. Whatever way works best for you, I am okay with. One of them will work out eventually. Okay, it is about time for our second break, so let's do that. It is 7:19. We will come back at 7:29. So, in our last hour, unfortunately, we saved the best for last. We need to look at word problems. One of the reasons we want to solve equations is because we need them to solve many word problems. Like I've said before, life is a word problem, so we're going to have to get used to them. One of the toughest skills in math is looking at a situation, a set of words, and picking out the relevant information and deciding what to do with it. So I totally understand people struggling with word problems. Unfortunately, you're not going to like the next statement. The only way to get good at them is to do them. As we've mentioned before, math is about patterns. Well, the same thing is with word problems. The more word problems you do, the more you start to see similarities from one to the other. And you start to see those patterns develop so you can look at a problem and figure out how to do it. So we're going to start out with some really simple ones. Now, with the simpler word problems, the problem people have is they look at the problem and they know how to get the answer. They don't need to write an equation. So I'm going to ask you to be patient with me on these first few, because I know pretty much all of you could solve these without writing an equation. But we're going to write the equation anyway just to practice it and get good at it with the easy problems. So you have to pardon my handwriting. I'm going to sketch these out kind of fast. Let's say you put 1/4 of your pay into savings. How much did you earn in a year where you saved $19,500? Now, again, I realize most of you could punch this in the calculator and have an answer in a few seconds, but I want to walk through the process of writing an equation here. You put 1/4 of your pay into savings. So what that means is 1/4 times your pay equals what goes into savings. It's often easier to write an equation before we look at any of the numbers in the problem. So now the $19,500, does that go in for P or S? It goes in for S. It is a savings. So that's going to go in here. So we can put that into our equation. 1/4 times P equals 19,500. Now to solve the equation, we're back to taking it apart. Now because of the fraction in here, this one's a little bit tricky. We actually have two options. P has been multiplied by 1/4. So we can either divide by 1/4, or we could, dividing by 1/4 is the same as multiplying by 4 over 1, or multiplying by 4. So we're going to multiply by 4. 1/4 times 4 cancels out, leaving us with P. 19,500 times 4 is 78,000. That was a good year. Okay. Any questions on how we put that one together? Okay. So next, Ted sells sweatshirts for $23 each. Now I'm going to pause there before I even look at the rest of the problem. If I want to know what his total sales are, his sales is going to equal, actually I'll put T for total here. Total sales is going to equal $23 times the number of shirts he sells. Now the rest of the problem is, how many sweatshirts does Ted sell to gross? Gross just means your total sales. $3,381. So the 3381 goes in for T or S? T, that is the total sales. How do we solve this? We're going to divide by the 23. So we have F on that side. 3,381 divided by 23 is 147. Works for me. So Ted sold 147 sweatshirts. Does that make sense? Okay. Yeah. Let's say Pat sells 18 more cars than Peyton. Now let's look at that for a second. What is that telling us? Of course, I did Pat and Peyton. That really is silly. We're going to call Pat X and Peyton Y. One of them has to have 18 added to it, doesn't it? Which one, Pat or Peyton? Which one is smaller? Which one sold fewer cars? Peyton. So it's going to be Y plus 18. Peyton is the one that gets 18 added to it because they were the smaller one. To make them equal, you have to add to the smaller one. So Pat is equal to Peyton plus 18. How many did Peyton sell if Pat sold 31? Well, where does the 31 go? X or Y? X. That is Pat. What do we do from here? We subtract the 18. We get 13 equals Y. So Peyton sold 13 cars. So far, the type of problem we have done has been typical of this form. Two items equal each other. A equals B. That's our main type of problem, but there are two other types of problems we can run into. We can run into A plus B equals a total. Two things add up to make a total. Or we can have A minus B equals a difference. Two things subtract to make a difference. So back to it. So let's look at some problems that are some of these other types down here. So we're going to take a step up in difficulty. Let's say that Kim sells, we're going to stick with car sales since that's working for us. 7 more cars. I want to be smart and not use another K. 7 more cars than Mike. If they sell a total of 51 cars, how many did each sell? So here, this is the type, is it adding up to make a total or subtracting to make a difference? There's one key word here, total. So these are going to be adding up. There's a total of 51. Whenever we see a total of a certain number, that's usually 2 or more things adding up to make that number. So we have Kim's sales plus Mike's sales equals 51. Now we can't have two variables, so there's got to be a relationship between them. We're going to have Kim and Mike. One of them has to be expressed in terms of the other. Well, if we look up here, Kim sells 7 more than Mike. If I were going to write an equation, more than means added to, right? 7 is added to something. Which one would the 7 be added to? Mike. So we're going to let Mike be M. Kim is going to be M plus 7. 7 more than Mike. If we were writing an equation, Kim would equal Mike plus 7. Right? You add to the smaller one. So now we can use these two up here. Kim is M plus 7. Mike is M. Now we have to be careful here. The M appears twice. Remember that M by itself is really one M. So do we have to get rid of one of the M's or do we combine them? Combine them. They're on the same side of the equal sign. So 1M and 1M make 2M. We still have the plus 7, and that equals 51. Now what do we do? Subtract 7. So 2M equals 44. And then divide by 2. So M equals 22. All done? No, we have to actually answer the question. We found M equals 22, but we have to make sure we answer the question. The question is, how many did each sell? Well, M is the number that Mike sold. That is 22. We still need to do Kim. Well, we can do 51 minus the 22, or Kim is M plus 7, so 22 plus 7, 29. Now we can double check it by doing it the other way. 51 minus 22 is also 29. So it works both ways. Well, there's another form that's similar to that. That might look like this. Sam sells for, and we're still sober. Sam sells 4 times as many cars as Pat. They sell a total of 130 cars. How many did each sell? So again, we have the keyword total. So something adds up to 130. Sam's sales plus Pat's sales add up to 130. Now we need to figure out some variables to represent this. So we've got Sam and Pat there. And the way I usually think about this is I'll put Sam on one side and Pat on the other side of the equation. They're not equal, are they? What do I have to do to make them equal? Sam sells, this time we're not adding something to one of them, we are multiplying 4 times. Which one gets multiplied by 4? Pat, because Pat sold the fewer. So Sam's is 4 times Pat's. So what that means is we're going to use 4 times P for Sam. What are we going to use for Pat? P. One of them gets to be themselves, the other one is expressed in terms of the other one. Now what? What's Sam's sales? 4P. Plus Pat's is P equals 130. Now again, make sure you remember that this is a 1P here. It just says P, but it really is a 1P. So then what? Combine them. 4P and 1P make 5P equals 130. And then divide by 5. Perfect. P equals 26. Now again, we have to answer the question. P equals 26. That's how many Pat sold. We have to do Sam. 4 times 26 is 108. That's not right. 104. Thank you. Yes, that's probably pretty good for Sam. Any questions? Okay. Let's say Tom sold 3 times as many cars as Kim. Tom sold 26 more cars than Kim. How many did each sell? This problem's a little weird at first because it looks like I gave you 2 pieces of information that should be given in the first sentence. There's 2 different equations that we have here. Tom sold 3 times as many cars as Kim, which means Tom was 3 times Kim, right? There's also Tom sold 26 more cars than Kim. That'd be Kim plus 26. So what I'm going to do is this. I've got Tom and Kim. I can use either one of these equations. I'm going to use the top one. Then we're going to come back and do it the other way. But if I use that top equation, this is going to be, Tom is going to be 3K and Kim is going to be K, right? So now I'm going to use that in the bottom equation. Tom becomes 3K, Kim is K, plus 26. What do we do from there? Yeah, we subtract the 1K, we get rid of one of them. So this is now 2K equals 26. Then we divide by the 2. Perfect. So K equals 13. Which means, come on. Yeah, Kim is 13, and Tom is 3 times 13, or 39. Do they have a difference of 26? Yes, they do. Now, some people might have seen this better the other way, using the bottom equation first. So Tom is K plus 26, and Kim is K. So then we'd have to use the top equation up here. T equals 3K. Only we're going to have to replace T with K plus 26, right? Well, look, this equation and this equation. It's the exact same equation. I don't know why I put a 6 there. That's a K. Get out of there. There. Any questions? So as you can see, there are often more than one way to break down these equations. Now, a basic equation that we have is total revenue is equal to price times the number sold. We saw this in one of our first examples with the sweatshirts. So we sell $3,381 worth. How many do you have to sell at $23? Well, we can use this in a little bit more of a complex situation in this next equation. So Sam sells t-shirts for, let's say for $16 each. And hats for $8 each. If $1,760 of merchandise is sold, how many of each did Sam sell? This one's a little trickier. It's still price times the number sold equals revenue. And what we have here, the 1,760, is revenue. But we have two pieces of revenue here. We have the money or the revenue from t-shirts plus the revenue from hats is going to equal that total of 1,760. So we have to figure out some way to express the revenue from t-shirts and the revenue from hats. So we're going to start out dealing with that. How do we want to express the number sold? Well, there's a relationship between t-shirts and hats that I did not give you. I should maybe tell you that. Let's say Sam sells, how many items do I need here? 160 items total. I knew that problem seemed a little short. So if I tell you that Sam sells 160 items total, now we can get that relationship between the two. If I pick one of them to be X, I'm going to pick the number of t-shirts sold to be X. How many hats have to be sold? Well, let's say I put in a number here, and I'm just going to chalk this one in. If I told you that 100 t-shirts were sold, how many hats were sold? 60. How did you get that 60? Yeah, 160 minus 100 is 160. Well, we don't know that 100 of them are 100 t-shirts were sold. We know that X of them were sold. So the number of hats sold is 160 minus X. So we have X t-shirts and 160 minus X hats. Next, we need to look at the revenue or the dollars for each. Revenue is price times number sold. What's the price of the t-shirts? $16. How many were sold? X. So 16 times X, or 16X, is our revenue from t-shirts. How about for hats? What's their price? 8, the number sold. 160 minus X. So now over here in this equation, we're going to replace the revenue from t-shirts is 16X plus the revenue from hats, 8 times 160 minus X. And that's going to equal 1760. Now what? Okay, we see the parentheses. There's nothing to do inside of it. So we're going to distribute the 8. 8 times 160, 1,280. 8 times negative X, negative 8X. Now we still have this 16X up here. That's a positive 1280, so I'm going to put a plus in front of it. Still equals 1,760. We are going to combine the x's. Perfect. 16x and negative 8x combine to make 8x. So they're on the same side, so we can just combine them. So we have 8x plus 1,280 equals 1,760. Now what? Perfect. We subtract the 1280. So that's gone there, leaves us with 8x. 1760 minus 1280 is 480. Now what? We divide it by 8. X equals 60. Well, again, we have to answer the question. The question was, how many of each was sold? Well, X is 60. That's the number of t-shirts. So the number of hats had to be 160 minus 60, or 100. What do you think? Not bad? Time consuming? Yes, it is time consuming. I'll give you that. So let's stick with it. Pat's going to sell. Oh, what does Pat want to sell? Now let's say he's going to sell shorts for $8 each and sweatshirts for $16 each. If Pat sells 4 times as many sweatshirts as shorts for a total of $1,440. How many of each did Pat sell? A very similar question. Once again, we're going to have revenue, dollars for shorts, plus the revenue, or the dollars for the sweatshirts. Okay, cram that together because it's a long word. Is going to equal our total of 1,440, 1,440. set up a table here again to organize this. We have our shorts and sweatshirts. The first thing we need to find is how are we going to represent the number sold. Pat sells 4 times as many sweatshirts as shorts. Which one has to get multiplied? The shorts is the one that sold fewer, right? So shorts is going to be our variable. I'm going to call it X. Just because I'm tired of writing S's so they don't look like 5s. Sweatshirts is then going to be 4X. There's 4 times as many. Our revenue, which I'm just going to put a dollar sign there. How do we express revenue again? Price times the number sold, right? So for shorts, it is $8. So 8 times X is 8X. For sweatshirts, it was 16, right? So that's 16 times 4X, which is 64X. So now over here, the dollars from shorts is going to be replaced with 8X. Plus the dollars from sweatshirts, 64X. That equals 1,440. And then, perfect. 8X and 64X, 72X equals 1440. And we divide by 72. X equals 20. Well, now what? We plug it back in. X is 20, so there's 20 shorts sold. 4X will be 4 times 20, or 80 sweatshirts. So a couple of different styles of problems. One last type of problem I want to show you before we're done here. And this is a problem, again, where I give you a set formula, but a little bit more complex than the ones we have here. I'm going to give you the simple interest formula. The simple interest formula is the dollar amount of interest is equal to the principal times the rate times the time. You may have heard that before. By the end of this semester, you're going to hear this one a lot. I equals PRT. If we have a loan that builds $240 in interest in a month, at a rate of 0.08. Find the principal. Okay, now, in this type of a problem, the dollar amount of interest is in dollars. The principal is also in dollars. The rate, it's a decimal form of a percent. 0.08 is actually 8%. The time is always given in years. So when I write this out, do I know the dollar amount of the interest? $240 in interest. Do I know the principal? No, that's what we are looking for. Find the principal. Do I know the rate? 0.08. Yes, I know the rate. Do I know the time? 1 month. Well, we set up here time is in years. So time, 1 month is 1/12 of a year. So now we could go through the trouble of combining those. It would get really ugly. 0.08 times 1/12 is going to be 0.0066666666. Goes on forever. So what we're going to have to do to make this work, if we try to write that down and punch it back in, we're going to have a round off error in our answer. So we have to keep it in your calculator. So I do have to combine those. 0.08 times 1/12. 0.006666. So I'm going to write that down. So 240 equals P times 0.00666667. Notice, however, I did not clear my calculator. To solve this, to solve this, what do I have to do? I have to divide that number there, that ugly decimal. So now that would leave P here by itself. I have to find this over here. Now, notice again, I did not hit clear on my calculator. I'm going to type in the 240, and all of your calculators, if you have a scientific calculator, have this ability. There's an answer key. It says ANS. It's usually down by your equal sign. You're going to hit divided by, and then it is the second ANS. What that is telling the calculator to do, we have 240 divide by the previous answer, that 0.006666. It gives us exactly $36,000. That little trick with the answer key is one that's going to be very helpful in a lot of different places. So let's do another example with this simple interest formula of how we use that key. So I equals PRT. So let's say 1 month interest of, let's see, $160. Principal of $24,000. Find the rate. So I is 160. P, 24,000. R, don't know it. That's what we're looking for. T, 1/12. Now in this case, it's actually going to work out to be an even number, so we could write it down, and we're not rounding anything off. But on the right side, before we solve, we do need to combine 24,000 times 1/12. 24,000 times 1/12 is actually just 2,000. But I'm going to put that in my calculator anyway. 24,000 times. Now you guys have a fraction key which will work. Otherwise, for 1/12, I can just do times 1 divided by 12. Gives me the 2,000. Now I'm going to leave that in my calculator so I don't have to punch it back in. My next step is going to be divide by the 2,000. So R equals 160 divided by 2,000. I'm going to type in 160 divided by second answer, 0.08. So my rate was 0.08. If we wanted to convert that into a percent, it would be 8%. Any questions? Okay, I think you guys have suffered enough for one night. You need to know there is a new quiz. I know since the beginning of class, but we're going to mention it again. This is quiz 1, which opened at 3 o'clock today. It will be due at Wednesday. This is Wednesday. Last year, this class was on Tuesday all the time, so I'm used to saying Wednesday. It'll be due Thursday at 11:59 p.m. There's also a new homework. Homework 2, which will be due next class, so next Wednesday. If you guys want to take the next 7 minutes to get started on your homework or finish up other homework, you're welcome to. Otherwise, we'll see you next week.